Hello, this is Unit 9, Part A. This is the first segment of the cryptography part of the UCLA Extension Fundamentals of Security class. The topics we're covering include terms and definitions, what is the terminology that we use in the field of cryptography, the basic process of encryption, how we take something that is clear and understandable called clear text and turn it into ciphertext and turn it back into clear text, the components of a cryptographic system, and then deal a bit with the difference between a public or asymmetric key system versus a private or symmetric key system. What's cryptography? Cryptography comes from the words for secret and writing, and this describes very well what the field is about. It's about writing in secret such that you can convey a message to somebody, but somebody in the middle who gets that message can't figure out what it says. It's the art of keeping messages secure. You're exchanging a lot of small secrets for one big secret. The thing about cryptography is it doesn't actually create security. It just changes what you have to secure. Instead of having to keep the entire message secret, you encrypt the message and then you have to keep the cryptographic key secret. So you're taking a big thing that you have to keep secret and changing it into a small thing that needs to be kept secret. Where is cryptography used? It helps provide authentication. Possession of a cryptographic key and verification that you own this key can help as an authentication method. You can use digital certificates, for example, as kind of a token, something you have to authenticate yourself to a system. Data integrity. Cryptography can ensure that the data that was transmitted by the sender is the same as that received by the recipient, that nothing has been modified, changed in the middle. Privacy or confidentiality. You can use cryptography to keep messages secret. You can make sure that unauthorized individuals can't read your messages. And then finally, non-repudiation. It is a cousin of authentication and data integrity. Non-repudiation means that if an act is taken by someone, that person can't later then repudiate or state that they never in fact did that their identity is irrevocably associated with the action, and it is non-repudiation. It means that you have a protocol or a mechanism whereby if something is done, the authenticated party doing it has to take responsibility. They can't later on and say, well, something went wrong in a system and it wasn't really me, because you've got something very solid that says that folks did something, therefore they can't repudiate. Where is cryptography used? Secure web access. Anytime you use a website for e-commerce, or hopefully whenever you use it for reading your email or doing anything confidential, you're using SSL or TLS. This is a whole cryptographic system that ensures your browser talks to the server securely, that any data transmitted between you and the server can't be intercepted or changed by a third party without detection, and that you as the individual wielding the browser knows that it's in fact coming from the website. So it's this whole complicated security thing that allows you to trust the information you receive from certain secure websites. It's what makes, for example, internet banking possible. IPsec and any other VPN protocol. You know, if you're out in the field and you're logging into a wireless access point at some hotel somewhere and you need to get a secure connection to your home network at your office and you need to be on your office network, virtual private networks enable this. And virtual private network protocols, specifically IPsec, make heavy use of cryptography to ensure that you can talk confidentially with your home office and they know that it's really you that's doing the talking and vice versa. Wireless access security. Wireless access points, 802.11 and any sort of wireless protocol, suffers from the distinct disadvantage that anybody with a radio and the ability to decode the messages can sniff the messages and possibly inject bad traffic. So over the years there have been many attempts to use cryptography to leverage it to make that process more secure. Varying degrees of success means that something like WEP, for example, with a wired equivalent privacy, didn't do very well. It was broken within a few years, whereas the more contemporary examples tend to work much better. Full disk encryption. This is something that if you have a corporate assigned laptop, you probably have. You boot up your laptop and you have to enter this full disk encryption password, and then Windows or whatever you use starts to boot up again. Full disk encryption relies on that password to decrypt the contents of your hard drive. If that password isn't correct, nothing else happens. If someone steals your laptop, pulls the hard drive, and tries to insert it into another device and read it, they can't. It's encrypted. They can't do it without the password, which is in effect a cryptographic key. And in code signing, when you download software, when you install software, oftentimes the code itself is signed to verify that that software is genuine and came from the party you in fact purchased or acquired it from. There are many authentication methods like Kerberos, Radius, and CHAP that use cryptography for ensuring the identity of the endpoints, for ensuring that the authentication exchange is kept confidential and can't be modified illicitly. Where is cryptography used? Cryptographic definitions. Cryptanalysis is a science of uncovering secrets. It's the opposite end of cryptography. Cryptography is the art and science of creating secrets. Cryptanalysis is the art and science of taking things that are secret and attempting to break the codes. And then you have cryptology, which is the mathematics behind cryptography and cryptanalysis. It's a very exotic field. It's a very difficult field involving a lot of discrete math, information theory, etc. A lot of graduate level mathematics is involved in cryptology. A lot of intelligence goes behind it, designing cryptographic systems, making them secure, and alternatively finding out good ways to break these systems. Basics of cryptography. Plain text. You start with plain text. That's your in the clear message. That's the stuff you want to encrypt or keep secret. It's your message, your pictures, your videos, whatever. Ciphertext. You take that plain text and you encrypt it. You change it into something that a third party can't read, doesn't know what it is, and can't figure it out. That's ciphertext. You convert plain text to ciphertext, and then the recipient has to convert the ciphertext back to plain text. The key. It's a secret or protected value used by the encryption algorithm to create the ciphertext from the plain text. You have an algorithm, which is a mechanism. You put into that algorithm the plain text, and then given a key, you generate the ciphertext. A different key will generate different ciphertext. The key is what has to be kept secure. The algorithm is the method used to encrypt plain text. The method is not assumed to be secret. There's no such thing as a credible crypto system where it's based on a secret method. That just doesn't work. Key definitions. Definitions involving cryptographic keys. The key space is a set of all possible keys for a given encryption algorithm. If your key is, say, randomly generated and 8 bits long, then you've got 2 to the 8th power possible keys. Key spaces are defined in terms of number of bits, because information in a computer system is defined as a certain number of bits. The more bits you have, the bigger the key space. Key management. That's a process of generating, distributing, storing, and destroying cryptographic keys. It's very important to cryptography. Keys don't magically appear somewhere for their use. Someone has to create them. Someone has to get them to the parties who require them. They have to be stored securely. And when they're no longer needed or become obsolete, they have to be destroyed in such a way that they aren't left around to compromise the system. Types of ciphers include a permutation cipher. This is a cipher that shuffles or recombines the elements of plain text. These elements are encoded symbols. They can be characters or they can be bits. In most computer systems, the elements of plain text are bits. But oftentimes, if you're doing crypto systems by hand on a piece of paper, you can make the elements characters. But for any real crypto system in any real computer, it's a bit that you're shuffling. So what you're doing is rearranging stuff in the plain text in a certain manner such that the ciphertext is indecipherable to somebody who doesn't know how you did it. A substitution cipher, on the other hand, takes the plain text and replaces it with something, again using a specific algorithm, and again the replacement is done with a key. So you can shuffle things around or you can substitute them, and most real ciphers use both of these together. Here's an example of a permutation cipher. You take the initial plain text, which in this case is the quick fox. I wanted to say the quick brown fox, but there's not enough room on the slide to do that. And you know, one of the characters is of course a blank. And this particular algorithm, you take two characters, move them ahead, take the following two characters, move them behind. This is 2 ahead, 2 behind. You could say in this case perhaps that the key is 2 and the algorithm is move x ahead, move the following x ahead of the previous one. So THE blank becomes E blank TH. This is a permutation cipher. The letters down here are the same as the letters up here. They're just shuffled around. Now a substitution cipher, you take the letters up here, and in this case, this is an example called the Caesar cipher, because Julius Caesar thought of this in an era when very few people could read or write to begin with. This was actually a very strong cipher. You would take each letter in the alphabet. The Romans did in fact have an alphabet and did have them in order, and then you shift it by 3. So T becomes W, E becomes K, or H becomes K rather, E becomes H, and then you treat the 27th letter of the alphabet as the blank as the 27th letter of the alphabet. So this shifts ahead 3 to become C. So you shift forward by C, and when you decrypt this, you shift backwards by 3 to get the original message. Very simple cipher, very easy to break, but in 20 BC or whatever, when very few people could read or write to begin with, it was effective. Now, related topics to cryptography include codes. There's a difference between a cipher and a code. A cipher, strictly speaking, is a replacement of a symbol with another symbol, where a symbol is just an arbitrary unit in a language. In the English language, these are alphabetical letters and characters in a keyboard. As far as computers are concerned, the unit is a 1 or a 0. Now, that's a cipher. A code actually deals with linguistic units. It replaces words and phrases with other words and phrases. Codes were used very frequently to make secret messages up until the era of cheap, ubiquitous computing. Diplomats in the Renaissance had code books where certain sensitive phrases were secretly translated into certain innocuous phrases. And they would use this for secret diplomatic messages that were conveyed to the home country, in the 14th, 15th, 16th century. So that's a code. A code deals with linguistic units. A cipher deals with symbols. And then you've got steganography, which is hiding a secret message in another innocuous message. We won't deal with this much in this class, but it's a way that you can hide a message in something that looks innocent. Like, for example, you can have a picture of a forest, and inside of that hide, secret instructions for committing some heinous crime. And you can hide it in such a way that somebody who has this digital replica of the picture of the forest can't figure out where you've hidden the message. Here's an example taken from Wikipedia, so it's public domain. We have an image of a tree, and hidden in that image is actually a hidden image. And you reveal it by removing all but the 2 least significant bits of each color component and a normalization. We take that image, we go through the method of unhiding, and we find someone's cat picture. They've managed to hide that picture of a cat inside the picture of the tree, just in a couple of significant bits. So this is an example of steganography. It's hiding things in plain sight. Cryptographic definitions, the basics. Plain text. You start with plain text. You then apply the cryptographic algorithm to the plain text with the key. So you take something that's a plain readable message. It could be a picture, could be an MP4 video, could be a text document. And you encrypt it using an algorithm and a key. Remember, the key has to be secret. The algorithm, you don't rely on the secrecy of the algorithm for the security of this. the end result is you have ciphertext. It's just a machine. You shove plain text in one end, add a key, and out the other end comes the ciphertext. Steps in managing cryptography. Cryptography isn't just a matter of generating secret messages. There are lots of things that have to go around it to manage it. You have key generation. How do you create secure cryptographic keys? This may seem, like a very trivial sort of thing, but it's actually a very difficult problem. How do you make something that's truly random and that can be used to ensure the security of the system? How do you get the keys to the folks involved in the communication? Key distribution. That's a very critical element. If someone can break key distribution, a bad guy can get a key, and your crypto system is completely gone. You also have plain text encryption. You take the plain text, this stuff here, and you turn it into something here. Can't be read, is under lock and key. You don't know what it is. The recipient has to be able to take that ciphertext and turn it back into the plain text. So you have a process here that obfuscates, but also has to be reversibly obfuscating. It has to take something that makes sense, turn it into something totally random, and then turn it back again. And it has to do it in such a way that somebody watching this thing from the outside can't figure it out. That's what makes cryptography hard. Now, the components of a crypto system. I'm going to go over this kind of briefly, but keep in mind, at the very bottom, you have what we call crypto algorithms. And these are things like the data encryption standard, RSA, Blowfish, AES, etc. These are things that you implement in software that takes basic units of plain text, turns it into ciphertext, and can turn it back. And then what you have is what we call cryptographic mode. Because data has different sorts of structures, you have different things you want to do with the encryption. Are you encrypting a file to upload it in batch? Are you encrypting a communication stream 1 bit at a time to send to a destination? Those are block and stream modes. So you've got different modes that use algorithms in different ways. You then have protocol. A protocol is a conversation. It's a way that two parties talk back and forth to get something useful done. Types of protocols include key exchange. I have a secret key. I want to get it to you. I have to go through a protocol, a defined set of steps where I talk to you. I ensure that you are who you say you are. We set up some mechanism where we can securely and secretly exchange the keys. We exchange the keys. We verify we've done that. That's an example of a protocol for key exchange. Protocols exist for things like signature verification, encryption, decryption, etc. And then at the top, as we've said in other classes, is the application, the thing that actually adds value to it, the thing that makes cryptography worthwhile. Do you want to send a secure email? Do you want to send your credit card number to a vendor over the internet and make sure nobody can illicitly sniff that credit card and make sure that the vendor actually accepts it and properly applies the payment and verifies it? These are applications. They rely on protocols. Each of these relies on multiple protocols. A protocol uses modes, and the various modes use algorithms. So this is how you build up your cryptography. Types of cryptography. We have symmetric or private key, so-called. The key to encode is the same as the key to decode. So both parties require the same key. Anybody can know what the crypto algorithm is. In fact, that's not even private knowledge. It doesn't add to the security. The key adds to the security. So I have to have the key, you have to have the key. Somehow I have to securely get the key to you. Well, the conundrum is, if I can securely get a key to you, why don't I use the same mechanism just to securely get the message? Why bother transmitting a key through a secure channel so you can encrypt a message when, if we have a secure channel in the first place, we can just send the message there too? Now, of course, the answer is sometimes a secure channel doesn't have the right characteristics for sending the message. The secure channel may be very slow, may have a limited bit rate. You can only send X number of bits and not an arbitrary amount of messages, etc. But that's a real issue. It's you have to find some mechanism outside of the crypto system for securely getting the keys to folks. Like a locked diplomatic package, or a hardened hardware device that has the key burned in ROM or something like that. So that's an issue with symmetric key. key to encrypt is the same as a key to decrypt. Now let's look at asymmetric or private key. This is a relatively newer one. It first became public knowledge in the 1970s, though various spy agencies claim they knew about it for decades before. In this case, the key to encode is different from the key to decode. So it's easy to transfer the key. If you want somebody to send you a secret message, you just give them the encoding key. Anyone else can have that encoding key too, but they can't decode the message using that key. You need something totally different to decode, and only you have that. So you keep one of these keys secret, and you hand the other one out to the folks you want to talk to. And that's the end of the story. It makes it very easy. And as long as the folks you're handing the encoding key to know that it really came from you and not from your evil twin brother or someone pretending to be you, then this sort of crypto system is very easy to use. So, and this is asymmetric or private key encryption. You know, the main private key system or asymmetric key system, or excuse me, this has to be public key. I made a mistake here, okay? Anyway, public key system is RSA. There's other ones too, but the RSA algorithm developed in the 1970s by three mathematicians having the initials R, S, and A is the main one in use now. And it involves certain mathematical problems where it's creating the problem is easy and solving it is hard unless you've got a secret clue. And that secret clue is the cryptographic key. So encoding something involves applying the hard mathematical problem. Decoding it, if you have the key, involves using the cheat to reverse the hard problem. But if you don't have the cheat, you can't do it. Here's traditional or symmetric private key. The first step is key distribution. You get the key. Whoever generates the key gets it to the other party they want to talk to. The next step is the ciphertext transmission. The party with the key takes their plain text, turns it into ciphertext, and sends it to the other party. First step is get the keys out. Second step is to transmit the message and decrypt it when you receive it. Now, asymmetric or public key is a little more difficult. You've got a key distribution step. You have a party that creates a key pair. One part of that key pair is private, meaning you've got to keep it secret, you've got to keep it guarded. The other part is public. You publish it, you give it to folks, and as long as these folks can verify it really came from you, they're good to use it. So, you've got your secret key, it's here, you keep it to yourself, you create a public key, you give it to everybody in this massive room party, cocktail party of people. Anybody can have the encryption key, only you have the decryption key. Everybody here can send you a secret message. This person here can't read the secret message sent by this person because they only have the encryption key. They don't have the decryption key. The encryption key and a decryption key are totally different. So message encryption involves these folks take a message, any one of them, they apply the key to the message, and you receive the message. And you take your private key, and you can decrypt it. Only you can decrypt it, because of course you kept this thing secure. And that's it for this first unit. We'll have units B and C coming up soon too.